Welcome to the Flow Computing podcast, and today we'll dive deep into the Flow Computing's PPU technology. And joining us today is Professor Dr. Jörg Keller, professor with the Faculty of Mathematics and Computer Science in Universität in Hagen. Professor Keller has done technical due diligence on Flow's parallel processing unit PPU. Welcome, Jörg, to the show.
Hello, and good to be here, and let's talk. Today we have multi-core processors, so processors with a larger number of cores to increase the computing performance. Now, for quite some time, those computing cores have all been the same. Then, some time ago, manufacturers have started to introduce processors with different types of cores, like ARM's Big Little technology. Still, all these cores have been independent of each other. Now, when we have code that can be parallelized, then it would be nice to have a number of cores that basically do the same and do this without the overhead that we get when each core is rather independent of each other. And this is where Flow's technology comes in and where the PPU cores come in. So next to the standard CPU cores, we have a set of PPU cores that are largely doing the same thing at some time and thus can speed up some code without each having to fetch their program for themselves, because they all do the same and they don't need to maintain all the structures that normal CPU cores have to do to run a program. So we have an easy way to parallelize with less overhead. And moreover, the PPU cores can be smaller than a typical CPU core, and so their power consumption will also be lower. If we have original code, this allows programmers to recompile with a compiler that is aware of Flow technology. So the compiler can detect all possibilities for performance improvements and turn them automatically into executable code. The programmer naturally also can fine-tune the source code with additional time effort. If we don't have the source code, we can still use a binary-to-binary translator that searches the original executable for code patterns that can be transformed into faster code when we have the PPU cores. A further benefit for these legacy codes can be obtained if operating system or programming system libraries can be recompiled for Flow computing. Then those will run faster on the PPU's cores, even if the application code itself is unmodified and just calls the improved libraries. Applications that are run nowadays quite frequently are applications that have to do with video. So the easiest thing might be video decoders, when we just play some video that has been pre-recorded. Those decoders typically exhibit a sufficient amount of parallelism, which currently is often not exploited or not exploited very well. On the other hand, we have a growing fraction of videos going from high definition to 4K resolution, and also we are seeing higher frame rates. So we need more processing performance, and this could be delivered by parallelization via PPUs without the need for much energy-hungry processors. The other side is production of synthetic video from scripts, for example, presenting avatars or explaining things to people without having pre-recorded videos. So the production of videos also needs computing performance in real time, which could be provided again through PPU cores, which are less power hungry than the usual CPU cores than we have today. So the PPUs, they do not exist alone. They have front-end cores, which are normal CPU cores. So when we use a well-known front-end instruction architecture of some current CPU, this simplifies the start when you go to a CPU plus PPU architecture. Existing codes for the CPU will immediately execute on the CPU cores, yet without performance boost on the PPU cores. I already mentioned the availability of a binary-to-binary translator for existing executables, and this can help just to speed up those applications, because then they can make use both of the CPU cores and of the PPU cores. When we also have a compiler and IDE, we can work with source codes that we have, and this will allow to experiment at different scales of time investment. We might start with an automatic detection of parallelizable patterns and run the flow compiler. And this might go with more and more time investment, recoding some things, up to hand-tuned kernels written specifically for the PPUs on the extreme end. So we have a scale of options here, and as the start is rather with a low hurdle, you just have to switch to a new compiler and IDE. That will make transition not too difficult, in my opinion. It's nothing that is kind of a wish for the future that we would like to have that, but it's technology that has already proven itself as doable and as feasible to make help such transitions possible. When we talk about latency, we really mean two things. For a whole application, we mean if its reaction time is real time or not. For a single memory access, we mean by latency how long it takes. In a classic CPU core, these two things are connected. A slow memory access, which cannot be overlapped with other computation, slows down the application, so the reaction time goes up. Flow's architecture is built to hide latencies through multiple fibers. So, a long memory access can be tolerated as its latency is hidden and does not translate into long application reaction time. So for latency, PPUs have decoupled memory access latency and latency in the application's reaction. And this is, I think, a good thing. So when we switch control from CPU cores to PPU cores by running fibers, there is a certain overhead. However, this overhead is much smaller than the overhead when we start further threads on a classic CPU. with multiple cores. The PPU fibers share a large part of their state, and they all execute the same code. So the startup time for fibers is much smaller than for CPU threads, and thus going parallel and handing over control to the PPUs will be much faster. As it is much faster, it pays off already for much smaller parts of the code that can be parallelized with PPUs but are not worthwhile to be parallelized on CPU threads, because there the overhead would be too large, giving the small workload. So after going to multi-cores, for some years now we see processors with different types of cores. For example, ARM's Big Little as an early example, where some cores are more powerful and also more power hungry, and some are slower and are more energy efficient. We also see cores or CPUs that have additional specialized cores, like crypto cores doing AES encryption or SHA-3 hashing. So they should provide high performance for a very special purpose. We also see all kinds of accelerators that provide computing power for a certain class of operations. And those accelerators appear both on the die and external. The most prominent among them are FPGAs and GPUs. Now, when we see this diversification, it's clear that manufacturers must take a somewhat difficult decision. They must decide what to bring on a die. How many power-hungry CPU cores, how many energy-efficient CPU cores, how many specialized CPU cores. In this slide, flows architectures with some CPU cores and a larger number of PPU cores is not exotic, but it wedges in this scenario as it has different types of cores, and the PPU cores are very efficient both energy-wise and both as they cover a large class of applications. Beyond, this architecture tries to avoid a number of disadvantages that other variants bring. High-performance CPUs normally target a broad range of use cases. So some accelerator or coprocessor should always be there. As PPU cores can replace quite a number of those, it can be a candidate for consolidation in this area. Beyond using only one type of accelerator, if you would name it as such, PPU cores show a simplified programming, because in the end they can be programmed with fibers like we used to program classical multi-core CPU cores, and we don't have exotic programming like in some classic accelerators. So PPU cores show promise to get this field into the next level and make it easier to access for a broad range of applications. Introducing a new type of core is always difficult. So success naturally cannot be guaranteed. However, PPU has at least one advantage. It comes at the right time. So industry must do something, because on the one hand, the requirements for performance go up and up. On the other hand, the operating frequency cannot be scaled up anymore for technology and energy reasons. Also, we cannot simply replicate more and more cores on a large multi-core die because they simply won't fit on that. So there has to be some way, and PPU shows a promising path where to go without being as exotic as having a very unconventional type of accelerator. So it might now be the right time to introduce PPU into industry and thus raise their attention more than it might have done 10 years ago. I mean, these ideas have been around for quite some time. I mean, it has developed already quite far, and there are patents and there have been prototypes. So it's nothing that has just been invented in the lab last year. On the other hand, 10 years ago, most people say, okay, we have 4 cores or 6 cores or 8 cores on our die, and that's fine. And only for certain scenarios, like more or less embedded systems, energy played the prominent role that nowadays it has for everything. Also, 10 years ago, most processors still were in computers. Today, most processors are not in classic computers anymore, but are in everyday devices like smartphones. So the scenario has changed a lot in those 10 years, but the types of cores that we have did not really. So already ARM Speak Little, to cite this example again, this looked like a large step, although you just had some faster cores and some smaller cores. They had the same instruction set and they had basically the same capabilities, and that was all. So PPU goes much beyond that because it's about integrated parallelization, and that is something that I have not seen so far.